Hello, everyone. Welcome to MIF++ seminar. It's a pleasure to introduce Lauren McHugh, who will talk about metal organic frameworks, the same MOFs as appeared in the latest Nobel Prize for Chemistry. So, Lauren, over to you.
Okay, hi everybody. I'm Lauren and I'm a lecturer in materials chemistry here in Liverpool. So I work on lots of different materials, but first and foremost, I'd say I'm a metal organic framework chemist. So this is sort of on the back of MOFs winning the Nobel Prize, and I'm just going to give you a bit of an introduction to what MOFs are, some things that they can be used for, and maybe tending towards some sort of future perspectives as well in these materials. And the slide clicker's not working now. Brilliant. So MOFs won the Nobel Prize this year. I hope you're all aware. So this, I think, is a long time coming, but the Nobel Prize was awarded for the development of metal organic frameworks just last month. So it was given to three researchers who are sort of pioneers in the field. So we've got Richard Robson, we've got Susumu Kitagawa, and Omar Yagi. So Richard Robson was essentially the first person to make a MOF. So back in 1989, he coordinated metal ions and linkers together and formed this framework structure with porosity. He didn't call it a MOF, but it was essentially a MOF that he made. So another person, Susumu Kitagawa, he is responsible for sort of taking it a step further. So he took these MOF materials and he actually showed that they could be used for things. So he looked at flexibility in these frameworks, he looked at function in the frameworks, and he proposed that they could be used for lots of different applications. And our third person who was awarded it is Omar Yagi. So anybody who has worked on MOFs is probably more familiar with Omar Yagi. He is generally termed the father of the field of metal organic frameworks, and he is responsible for definitely popularizing the field. So he called them MOFs in the first instance, so he's the one who actually coined the term metal organic framework. He also was responsible for some of the first sort of applications of these materials. And a lot of the stuff I'm going to talk to you about, reticular chemistry, isoreticular chemistry, etc., these were all principles that were sort of first explained by him. So three people got awarded this Nobel Prize. They're all massive people in the field, and if you've read any papers on MOFs, you'll probably recognize their names. So yeah, I think it's been a long time coming for MOFs to actually get the Nobel Prize. I'm very happy as a MOF chemist, and hopefully by the end of this, you'll see that they're good for a bunch of things. So what are metal organic frameworks? They are essentially framework solids or network solids, and they are made by coordinating metal nodes or clusters with organic linkers. So you can see the sort of prototypical MOF structure on the slide here, and you can modulate their properties in a bunch of different ways that we'll explain. So you can change the metal centers, you can change the linkers, and you can also introduce defects into these materials as well. So as you can see from the screen, they have this cage-like structure. So this sort of cage around here, this framework. And because of that, we have this large central void space in the middle, and we call this a pore. And because of that, we typically think of these materials as being porous materials. And because we have this pore in the center of these metal organic frameworks, they typically got very high surface areas, and that's very useful for a bunch of different applications that we're going to explain. So if you've seen a MOF before, you've probably seen it represented like this. So this is MOF 5. This is a very, very famous MOF structure that was discovered by Omar Yagi. So it's also called MOF 1, which is isoreticular MOF 1. We'll explain a little bit about that as we go through. But essentially, this is a framework that is zinc centers coordinated by these BDC linkers. So a BDC linker is 1,4-benzene dicarboxylate. And you get very familiar with these codes as you go through MOF chemistry. So BDC is used in many different frameworks. You have BTC, you've got all sorts of other ones. So there's another interesting way to describe MOFs. So this is probably a more simplistic way to describe it. I think it's, if you work on MOFs, it's a bit annoying to simplify it in such a way. But essentially, MOFs can have really high surface areas. So theoretically, some of these can have a greater surface area than that of a football field. And it's not wrong in a way. So if you think, they're really, really lots and lots of tiny little pores, really, really high surface areas. So technically, they do have a higher or similar surface areas to that of a football field. So it's a good way to explain to people when you're trying to explain just how porous these materials actually are.
Lauren, could I ask about the surface area? So how is it computed within a unit cell or over the whole infinite crystal?
So you do gas sorption for the surface area. So that's going to be in the whole of the material, and you will dose it with a gas in some kind of gas sorption instrument, and that will tell you the overall surface area. So it's going to be over the whole crystal.
Over the whole crystal. Yeah. Well, so look, it should be an infinite structure.
Yes.
Right? And by surface area, you mean the surface of these pores inside.
Yeah, the void space, essentially, I guess. Okay. Yeah.
Well, that void space is also infinite. You can see the periodic crystal. So I'm wondering how this infinite void space can have a finite surface area.
It is expressed per gram. Refinement, you see that?
Yeah, so
7,000
this here
per gram.
Ah, per gram. Yeah, that's what I was asking. So basically, per unit cell.
Yeah.
Per volume. Okay.
Yeah.
Fine. Thank you.
Okay. No worries. So MOFs can also be represented like this. So this is just another representation. So you've got this framework formed by these polydentate ligands or organic linkers coordinated to these metal centers. So this is a bit of a simplistic view of these materials, but it's just to sort of show you the general representation of how you'd make a metal organic framework up. So the linkers that we're talking about are typically carboxylate linkers. It's definitely not just carboxylate linkers that we use to make these frameworks. So carboxylate linkers are these kind of linkers here with these carboxylates on the end. So you can also have imidazolates, you can also have bipyridyls, pyridyls, etc. So there's an endless number of linkers that you can use to make these kinds of frameworks. So you also have these SBUs. So these are these little well-defined clusters of metal ions, and these are the repeating nodes in the structure. So this is essentially, you could represent it like this, and this would be a representation here. So this is a simplistic diagram of our MOF here with our metal nodes connected by organic bridging linkers. Obviously, it's a bit more likely to look like this in real life, where you've got these clusters. So in this case, you've got a zinc cluster coordinated by these BDC linkers like so. So this leads us on to the concept of reticular chemistry. So this is essentially where you're talking about all the different components from the nodes and linkers in a metal organic framework. So you've got a whole bunch of different combinations that you can use to make up different frameworks, and you can combine these in a variety of different ways to form these extended architectures. So these can all combine to form these extended architectures as so. So reticular chemistry essentially means that you can have a whole different bunch of these inorganic nodes, and then a whole different bunch of these organic linkers, and coordinate them in a controlled way to form a vast number of different structures. And this is also where computer or computational prediction comes in handy as well. So people have used a lot of computational studies to try and predict the formation of metal organic frameworks. So you can use computational methods, predict the frameworks, and then actually go away and try and synthesize these materials as well. So there's a whole different bunch of metal organic frameworks out there. This is a very, very non-exhaustive list here, but essentially you've got MOF5, one of them. So we can see that we have this zinc cluster coordinated by a BDC linker to form the material that we saw previously. You can also have copper clusters. So this here is a copper cluster coordinated. This is actually another carboxylic acid up here, just hidden slightly. So this is another very famous linker that we use in MOF chemistry called benzene tricarboxylate. But then you can also see that the same linkers start to show up again and again. So here we've got our BDC linker again, this time coordinated in a chromium structure to form something called MIL101. And then we have other structures here where we've got BDC linkers. We also have extended linkers as well. And then we have big, much more functionalized linkers. So this is sort of reticular chemistry in a nutshell, where you can have lots of different SBUs combined to lots of different linkers to form lots and lots of different structures. And essentially, there's millions and well, there's many MOFs out there, and you can find many things in many different ways to form many different structures. So this leads us on to actually trying to engineer these materials a little bit more. So to do that, we do something called isoreticular chemistry. So this is where we keep our inorganic units, so we keep our metal cluster the same, but we change the linker that we have inside the framework. So this here is the representation of that MOF5 structure that we saw before. So we've got our zinc clusters coordinated by our benzene dicarboxylate linkers. But if you keep those zinc clusters the same and you extend the linker like so you've got one with 3 benzenes in here, you can have the same overall structure, but a different pore geometry, so a different pore size. And similarly, you can keep it the same again, but you can actually functionalize the linker in this case. So here we've got a much more complicated linker. And this again changes the properties actually within the pore as well. So this just allows you to keep the same overall topology, but change the pore diameter, the pore, and lots of different things about the pores. And it allows us to modulate the pore size and also the chemical environment of the actual guests that go into the framework. So I just wanted to highlight a few studies for people actually within the department. So it's worth mentioning these are not MOFs, hence the name, non-metal organic frameworks, but it is just to show the concept of isoreticular chemistry and how it can actually extend to related framework materials. So these are a series of essentially porous salts that were discovered by Andy Cooper's group and published just last year. And they're a similar concept to metal organic frameworks. So in metal organic frameworks, we have these inorganic linkers, these inorganic nodes connected by organic bridging linkers. In this case, you've got organic cations coordinated to halide anions to form these porous salt type structures. And essentially, you can do isoreticular chemistry with these as well. So you can keep the same architecture of the overall framework, but just change the linker in such a way. So it's just to show that isoreticular chemistry can be shown across a lot of different kinds of framework materials. You've also got other related structures to metal organic frameworks, and these are called COFs, or covalent organic frameworks. As the name suggests, they also don't contain metals, they're purely covalent structures. So these were discovered maybe 20 years or so again by Omar Yagi, and this is sort of a couple of the first ones. So you've got COF1 and COF5, and these are based on sort of boronate type linkages. And essentially, these are also highly porous structures. They're very regular structures. They're very stable structures. But one thing I will say is they're not particularly crystalline. So when we talk about metal organic frameworks, typically they're nice and crystalline when they form. COFs are not really. If you've worked with them, you will certainly know that. And this field has also gone from strength to strength. There's many people working in the field of COFs as well. And just last year there was COF 999 published. And this is an olefin functionalized COF, and it's actually been functionalized with azides. And this just means that it's made it really good for absorbing carbon dioxide. So again, it's just showing that you can do similar kinds of chemistry with related frameworks to metal organic frameworks, and you can functionalize them in lots of different ways, in this case for carbon dioxide capture. So this then leads us to another class of metal organic frameworks this time called zeolitic imidazolate frameworks. So these are materials that have got a zeolite type topology. So they are still metal organic frameworks, but they're a subclass of metal organic frameworks. You may have heard of these before, I'm not 100% sure. So in a zeolite, which is a purely inorganic structure, it's an aluminosilicate porous material. You've got this silicon oxygen silicon bridge, which is about has an angle of about 145 degrees. These zeolitic imidazolate frameworks have got a similar kind of angle, so between the metal, the imidazole, and the metal of about 145 degrees. So we define them in terms of having zeolite type topologies. So they would be described as having, say, a sodalite topology, etc. So they're a little bit like zeolites in that respect. There's many different kinds of ZIFs out there. They're also used for many different things in the same way that MOFs are. They can be used in catalysis, drug delivery, gas sorption, separation, etc. And we'll explain a little bit more about these, about how you can actually take these forward and make new kinds of non-crystalline materials with these as well. So this is just one of the most famous ZIFs out there. This is called ZIF 8, and this is again got the sodalite type topology. So this has just got methyl midazoate linkers in the structure, and this is sort of what the crystal structure of a ZIF would typically look like. So I put this slide up because it's got some common MOFs on. I'm not saying that these are the most common MOFs in the world at all. There's many other ones out there that people use a lot more. But essentially, I put these on because I have them with me. So I just wanted to show you like what MOFs actually look like. So these were very kindly donated by my students. So the first one, this yellow one, is called NU1000, and this is a zirconium-based MOF. So the color actually comes from the linker in this framework. It's also an absolute nightmare to work with because it stains everything in sight yellow. We've got the blue one, which is H+1. So any guesses for the metal here? It's copper-based. And then we've got this ZIF structure. So we just mentioned ZIFs. This is a mixed linker ZIF called ZIF 62. So we have imidazolate and benzimidazolate linkers in this structure. And it's colorless or purple, depending on whether we have zinc or cobalt in structure. So I will pass these around and you want to have a look at them. So sometimes you get powders, sometimes you get gorgeous big single crystals. It depends on how you synthesize them, and it depends on, I don't know, how the MOF is feeling when it forms. But you get lots of pretty colors, and personally I think it's a lot better than zeolite chemistry because usually you just make white. So we make some pretty colors in metal organic framework chemistry at least. Okay, so how do we make MOFs? There are many different ways to synthesize a MOF. I was trying to make a slide yesterday and I was like, I can't think of like how to express this. So I stole an image because I thought it was quite nice. So there's lots of different ways represented here. Some of these I probably wouldn't do, but people certainly do them to make these materials. You can make them in a reflux. So I'm not going to show you effects of a reflux. You've all hopefully done some, maybe kind of a chemistry degree. So you've maybe done that before. So there's microwave synthesis, which is like a really rapid way to synthesize things. I think I did that once during my PhD. You've also got solver thermal synthesis and mechanochemical synthesis. So solver thermal synthesis is typically done in a solver thermal jar, such as the one here. So basically you just put this in an oven, seal it up, and then under pressure, you will hopefully form some nice, pretty crystals. You can also do mechanosynthesis, which is my favorite. So basically you put everything into a jar with a very small amount of liquid. You shake it at really high frequency. You basically like beat it up for like 30 minutes or something. And then you end up with a nice powder at the end. So it's a really, really efficient way of synthesizing materials. And if you work on materials, I would probably try synthesizing many of your materials mechanically, because you might just find that it actually works. In terms of MOF characterization, there's a lot of different areas. So I could do a separate lecture on all of these. I'm not gonna, so don't worry. But essentially, when you make a MOF, the first thing you're typically gonna do is single crystal diffraction or powder diffraction. So this is gonna give you an idea of the crystal structure if you actually make a crystal big enough. And it's also going to tell you like whether the thing you've made is pure and just how crystalline it is. So we'll see a bit later that sometimes PXRD will show you a hump because it's not crystalline. Sometimes you'll get really nice peaks in your pattern, like here. You can do IR, pretty sure you've all done IR at some point. This is going to give you a bit more of an idea about the functional groups in your structure, and you might want to know about, I don't know, a particular functional group that's in your material, and that's going to tell you something. You can also do SEM and TEM. So this is going to give you an idea of the particle size and the overall shape and morphology. Again, you've probably all done this before. EDX is going to give you an idea of elemental analysis and composition. Gas sorption analysis, really important because we are talking about porous materials. So in this, we'll put it inside our gas sorption analyzer, and you will dose it with a certain gas, whether it's nitrogen, whether it's carbon dioxide or something like that, at different values of relative pressure. You'll get an associated isotherm, and that will determine, based on the amount that you have put in there, whether something is high surface area, low surface area, and what kind of porosity it has. In terms of TGA, you can also do this to determine the thermal stability of your material. So this is another really important characterization technique because most of these materials have to be activated before you can use them for something. So you want to know that you're not going to kill your framework before you start using it. So TGA, you just basically like heat it up and then you'll see where your framework decomposes. So it's a really vital thing to do before you do any further. Yeah.
But what is activation in this sort of context?
Usually it's to take the solvent out of a sample. So if you want to do further analysis, so say you want to absorb a gas onto your framework or something, there's a fair chance that your framework is going to be full of water, it's going to be full of solvent or something. So we say activating as a way to activate it, I guess. So it just means you can then have like open metal sites or, you know, pores that aren't full of water for you to put other stuff into. So yeah, TGA, gas sorption, very important techniques to use when you are characterizing your MOF. There's other ones as well. We'll talk very briefly about PDF at the end and also a tiny bit about solid state NMR. So in terms of tuning MOF properties, there are many, many different ways that you can do this. One of them is by tuning the metal centers. So you can change the coordination, changing the metal centers. You can change things like catalytic properties. So like I was saying, if you activate something, you can have something called open metal sites. So this is where you've got under-coordinated metal ions, or metal atoms, sorry, and you can coordinate something onto that. So you could use it for catalysis, etc. Changing the organic linker is a really, really massive way to change your MOF, and that's typically how people will change the properties. And as it says here, there's essentially endless possibilities. So you can change the structure type. You can also keep the structure type. So we mentioned before about this isoreticular series. You know, you can keep the same structure type, but change the pore dimensions. You can also change the chemical environment inside the pores so they can be more hydrophilic, more hydrophobic. They can have more catalytic activity. And you can also introduce specific chemical functionalities based on the linker that you've put in there. You can also change it by synthesis and post-synthetic modifications. So, you know, just by modifications during the synthesis or after the synthesis can lead to sort of changed properties in your material. And you can also introduce defects into these structures, and many people have done that. There's many studies on defect engineering in metal organic frameworks. So I just want to talk to you about a few things that I worked on myself, because I guess it makes sense to try and put things into context. But this relates back to, I guess, metal centers and also linkers as well. So I'm very interested in water stability in frameworks, and this is a framework that I was looking at during my PhD called STAM, so St Andrews MOF. So essentially, it was based on this framework here, H+1. So this is the one I showed you, that blue one that I just passed around. It's really, really good for certain things. Copper MOFs are good for certain things like absorbing gases like ammonia, but they're not very stable long-term to things like humidity. So if you're going to use them in an application like putting them into, I don't know, a gas mask filtration system, something needs to give. So that's why this new series of frameworks were developed called the STAM series. And essentially they keep that same metal center, so this copper paddle wheel structure, but they change the linker. So we have this BTC, or I actually call it trimesic acid for H+1, and then we have a functionalized isophthalic acid linker to form our STAM series. So they've got the same copper paddle wheel structure. The linker and the way it's coordinated is a little bit different. Is that also going to be similarly affected by water? The answer was no. It led to a completely different mechanism, and quite a cool mechanism actually, called this crumple mechanism, but it was talking about this thing called hemulability in materials. So hemulability is essentially where you've got these sort of like sacrificial bonds within a structure. So in here, again, we've got our as-made sample. So this is our as-made sample. We've got all these waters in it. This is not very good if we want to coordinate something onto it like ammonia. We activate or we dehydrate our framework. And if you were to then put that back into water, if we were talking about H+1, over time that would degrade. But because we have these sacrificial bonds that form in the structure, when we reintroduce water back into our framework, these are selectively broken and we reform our framework as is. So this was a very interesting mechanism that we hadn't seen before. And we termed it this crumple zone mechanism because essentially, you know, you're keeping the core structure. So you're all right, but the front of your car is not. So these bonds are the front of your car and they're not. So we kind of likened it to that. So there is a bit of, something towards it. So that's one concept of, metal chemistry and also linker chemistry as well. You can also change the linkers. And again, this has got a very big difference in the associated structures. So here, this is another functionalized linker. So we have an amino-based framework. This still formed our stamp structure, all good. We find that if we extended the structure in a slightly different way, we ended up with a completely different structure altogether. So changing the linker can have very, very, very big effects on the structure type that you actually get when you have worked with the material. So I just wanted to put a couple of slides in here for another person who works in the department. These were very kindly provided by Alex Katsoulidis. So this is some work that was done in Matt Rosinski's group, who may be some of your supervisor, I don't know. And essentially, this was looking at ordered side chains in flexible MOFs. So here we've got this L amino acid side chain in a MOF, and here we've got this mixed L and D amino side chain in a MOF. And essentially, the way these ordered, so we had a bit more ordering, or they had a bit more ordering in this framework when we had this mixed system here. And it had this these pockets for binding. And essentially, it just meant that it was actually better at separating out hexane isomers. So you don't need to know too much about the chemistry here, but essentially, ordering of these side chains made it really good for separating out hexane isomers. So good for their functional properties. And then similarly, another little case study. So this was work actually done by Grace Farmer. Some of you might know her. She's just submitted her PhD now. But she was looking at these ordered straight and bent linkers and zirconium MOFs. So you've got these straight and bent linkers. And these were actually found by high throughput synthesis. So a bunch of high throughput synthesis was done to try and determine what structures might form. And then ended up with this sort of new topology here with these new types of windows formed. So this is essentially just showing that you can use high throughput chemistry, which some of you may actually be doing, to form new types of structures with new properties. And these were again very good for chemical separation, so separation of hexane isomers, etc. So in terms of general applications of MOFs, there are a lot out there. This is a very non-exhaustive list, and again, I could do multiple separate lectures for most of these actually, so we'll keep it brief, but essentially, they're very useful for things like catalysis especially, they're very useful as chemical sensors, they're extremely well used in gas storage and separation, drug delivery, and more, I'd say they're starting to get more used in battery technologies as well, and water purification. So if you're really interested in this, I highly recommend that you go away and have a look around the literature. Even just like drug delivery alone, there are hundreds and hundreds and hundreds of review articles on drug delivery and MOFs. And it seems like every MOF under the sun has been used to deliver some kind of drug. So, you can use it for therapeutically delivering gases, so things like nitric oxide. You can also use it to deliver, ibuprofen or something like that. So the possibilities are endless. But looking at a few just sort of absorptive applications of metal organic frameworks, one of the really big things when I started my PhD was vehicular fuel storage. I feel like it's kind of died down a little bit now. But essentially, because these are really porous materials, you can absorb a lot of gas or chemicals into these frameworks. You could theoretically fill your tank with a MOF and then fill that with hydrogen or whatever. And this would lead to enhanced hydrogen uptake because of, this surface area of these metal organic frameworks. And it would mean that you could store the gases at lower pressures in a tank than you would normally have to. So it does make sense. It does work. BASF, a big chemical company, had actually a little fleet of vans and they were filled with MOF, and they actually did sort of run around their plant for a while. But then they found that just because oil prices got lower, it wasn't commercially viable to use them anymore. So it does work, but again, we start to get back to if you have something that works better and is cheaper, is it actually going to be used? Another thing that's actually been commercialized is in the prevention of fruit overripening. So this was done by, I think it's MOF Technologies, and essentially this delivers 1 MCP, which sort of inhibits ethylene release. So, if you have like a banana or something and you sit that beside a bunch of apples, it gives off lots of ethylene, it over-ripens your fruit. So it's the same kind of principle here. So you put this MOF that delivers this thing that stops the ethylene or inhibits the ethylene, and it prevents your fruit from over-ripening. So it is a commercialized product, it does work, and I suppose it's quite a cool application. Another really well known one is in carbon dioxide capture. So this here is a framework called CALC20, and this is a commercialized framework. It's been made on massive scale now, actually. And essentially, this structure is a zinc-based structure. We've got these triazole linkers connected by these oxalate pillars in the structure. So it's got a high surface area, it is very water stable, it's quite easy to manufacture, and it can be manufactured on like the multi-ton scale, hence it's very interesting. And I think it was actually developed sort of in collaboration with Svante, who are a company, and they are actually looking at commercializing it. So why is it really interesting? Essentially, it can be used to remove or sort of capture carbon dioxide from flue gases. So this is a really interesting area because flue gases are unpleasant. They've got all kinds of mixtures of stuff in there, and your framework has got to be stable to all of them. It's got to be stable to water, it's got to be stable to, I don't know, any of the acids or whatever floating around in that gas. And this framework is. So it's been scaled up, and I think they've actually put it into a plant now. I think it was like 2023, they actually managed to make it on a large enough scale, and they actually did it on a large plant size scale. As with everything in MOF chemistry, the next thing you do is you mix it with something, you composite it. So I've done it myself, take them off and mix it with a thing. In this case, they mixed it with a polymer, so PIM1, you don't need to know about that, but they made a mixed matrix membrane. And essentially this just means that you then get the good properties of that polymer and also the MOF as well for things like separations, absorption, whatever you might want to use it for. So this is a really interesting framework, and I'd probably keep your eye out because I do think that it might actually go further. Another area is in water harvesting. So this is one people like to look at because it's an interesting area, admittedly. So essentially, this was sort of first hypothesized by Omar Yagi again, and a lot of people have gone into this now. But the idea is to take a box or something with a MOF inside it, and then because MOFs are very porous, during the night and high humidity, they'll pull the water in, and then you can release this during the day when it's drier and when you want water. So it's basically acting like a crystalline sponge in the same way that we actually typically describe metal organic frameworks. So the MOF that they used is called MOF 303. This is an aluminium-based framework, and it's got this really cool GIF actually from the Lawrence Berkeley National Lab website. And here you can actually see just how the water binds inside the structure, and then you can see that the pores are really, really full of water at the end of this animation as well. So you're basically like really saturating this framework, and they've gone through all the different values. I can't remember what they are off the top of my head. And I think this is one of the latest prototypes that they've done. They've made this like, I don't know, tube thing. And then they basically put this out in the desert and they let it do its thing and absorb water. And I'm sure more things will happen over time, and they'll keep refining this and make better prototypes over time. So another area that these are really useful for is in toxic gas absorption. This is an area that I love personally. So it's really interesting because it's showing that you're using metal organic frameworks to remove nasty things from the environment. So if you want to read more, there's many reviews, but this is quite a good one, published in 2020, and it shows like a bunch of different frameworks and a bunch of the different analytes that they are used to remove from the environment. So that can be water, it can be like ammonia, it can be nerve agents or anything like that. They've been used for many different things. So why would you do that? You could have just MOF sitting around waiting to absorb your toxic gases, but ideally you want to actually put it into something. So you could put it into, say, a respirator canister and a gas mask. So this is an activated carbon, not very functionalized, but porous. You could put it actually into like a suit of a first responder or a soldier or something like that. There's a bunch of different things that you can do with these MOFs. And this again is an area where they have been commercialized. So there is a company called MIF, owned by Omar Farha, and they have a couple of different product lines. They have one Sentinel, which is more for this like chemical warfare or first responders, putting it into canisters, fabrics, things like that. And then they also have this one called Ion X, which is where you can actually controllably release gases that are used in the semiconductor industry, like phosphine. So you don't really want to have those lying around, just in tanks. So you can controllably release these at much, much lower pressures. So definitely a very interesting use for these frameworks. And, they're gaining a lot of attention in this area. So that's kind of crystalline MOFs, but just for the last little bit, I just want to talk about the changing state of MOFs. So this title is shamelessly stolen from a really good paper from a few years ago called The Changing State of Porous Materials. And essentially, this is looking at the fact that most of the frameworks so far you've looked at have been crystalline. We're talking about crystalline materials. But what happens if they aren't crystalline? What happens if they're amorphous or they've got disorder in them? So this was quite nicely summed up in a relatively recent article. There's many different review articles now if you want to look at this in more detail. But essentially, this is showing that we've gone from inorganic systems and we've gone to this permanent porosity in MOFs, where we've looked at soft MOFs, so flexible materials and things. But now we've started to land at the point where we're looking at liquids, glasses, and amorphous metal organic frameworks. So it doesn't necessarily have to be a glass, it can be an amorphized framework. So here, this is just a sort of representation of a UIO 66, which is a very well-known metal organic framework. So if you basically bash this up in some way, if you press it, you ball mill it or something, you're going to lead to a disordered structure. Similarly, you can also have a glass, so you can have a crystal. You can make this into a liquid, so you've got this nice regular periodic array. Liquids, all of that is basically gone, and in the glass you have this kind of like halfway state in between all of them. So in all of these, we're talking about disorder within these frameworks, but they are still metal organic frameworks at the end of the day. So I couldn't do a talk without talking about MOF glasses, because it's what I work on now, and I really like glasses. But essentially, to make a MOF glass, you take that crystal, so all those lovely crystalline materials that we started with, you melt it, you get it to a liquid state, you don't heat it too high, and you rapidly cool it, and you form this glass. You can also, in some cases, ball mill them, but we're talking about the melting procedure here. So we end up with a glass, and it does still have that MOF structure, just in a very, very disordered way. So you can do this with zeolitic and metazoate frameworks. So those ZIFs that I told you about previously, they're very useful for a bunch of different things. They're also very thermally stable, so you can access this glassy state by heating them and then vitrifying them, and you get these dense structures like you can see here. So the glasses look a bit like this. They come in all sorts of shapes and forms. Unfortunately, I don't have this anymore, which was my pride and joy. It was the most pretty bit of glass I have ever made, but sadly it's been lost to time. But I do have a couple of examples of glasses if you want to look. They are a bit sort of like powdery, but you'll see they are kind of like quartzy, almost sandy when you have a look at them. So one's a bit more sandy and one's a bit more like little shards. So it depends on how the tube furnace is behaving when we make them, but this is essentially what you make if you make them off glass. So in terms of applications, still getting there, but they are showing some promise in gas absorption, gas separations. We have a slight problem that they're pretty dense frameworks, so all that porosity that we spoke about, we tend to lose when we make these glasses. But you can reintroduce it in some ways, and you can make membranes out of these materials, and they're pretty good for various chemical separations as well. So promise in this field, and hopefully it will go further. So when we talk about crystalline and non-crystalline frameworks, what do we actually mean? So in this crystalline framework that we spoke about before, if we did a powder diffraction pattern, it would look something like this, right? We'd have this nice crystalline pattern with lots of peaks in it. When we look at these non-crystalline frameworks, we're talking about very disordered systems, and we typically get a powder diffraction pattern that looks like that. It's fine because it tells you that you've made something non-crystalline, but you can't really get very much information after that. So PXRD is certainly helpful as like a fingerprint, but I wouldn't say it's the be-all and end-all for looking at these structures. So I'm not going to go into this in any detail, but it's just in case. Have you ever seen pair distribution function before? No? Okay. So if you ever do have a look at amorphous or non-crystalline materials, definitely something that you should look into. Essentially, this is total scattering. So have you all done powder diffraction at some point? Yep. So that's Bragg scattering, right? You're looking at the nice sharp Bragg peaks. Essentially, total scattering does it all. So you get the Bragg scattering and you also get the diffuse scattering. So it's a bit of a mess. However, you can extract data from the diffuse scattering on the short range order of materials, and that's what we need to look at for these disordered systems. You can also do it for ordered systems if you really want to, but it's not gonna tell you very much. So we can use this to characterize our amorphous solids, and you can also use it to characterize these disordered crystalline materials as well. So basically, you just do a Fourier transform on your total scattering data, and you end up with what's known as a pair distribution function. So I'm not going to go into a whole lot of detail, but just so you've seen it in case it ever comes up again. But essentially, the pair distribution function is the probability of finding two atoms with a separation distance of r. So this here means that we have a separation between two atoms of 1.42, separation between two atoms of 2.46, etc. This is just a carbon representation for simplicity, but essentially if you had this atom to this atom, this would be our first distance here, etc. So it's a really, really useful technique for looking at materials where you don't have long range order in structure. So definitely have a think about that if you are looking at anything that has disorder in your frameworks. And then again, the peak positions are going to tell you where your interatomic separations are, and then the area is going to tell you something about the coordination number. So what is this actually useful for? So you can utilize it with a bunch of different techniques. So this particular study was looking at the interfaces and MOF crystal glass composites. So this was work that was, one of the people who led it was Fred Blanc, who's another professor in this department. Are any of you working with Fred? No? So he does solid state NMR, which is another very important technique in MOF synthesis. So obviously we make solids in MOFs. Liquid state NMR is not very helpful unless you're dissolving a linker or unless you dissolve your framework up in an acid or something like that. So solid state NMR is really important because it's going to tell you about the structure. And it's very often used in combination with a bunch of other techniques, whether it be powder diffractions, and crystal diffraction, pair distribution function, etc. So you don't need to worry too much about what this study is, but essentially it's an inorganic glass and a ZIF composited together. So then Fred did this beautiful NMR, and essentially this was on a physical mixture. So where the two things were just mixed together, we can see that there isn't very much interaction between the ZIF and between the inorganic glass. And then obviously you've got this lovely interaction between the ZIF and the glass in our composite material. And this was beautifully looked at in combination with pair distribution function. So this is a pair distribution function of the pure ZIF. So we can see these atom-atom distances, so A to A here, whereas B to B here. So this is just correlating up all of these distances, and then also the distances within the actual composites as well. So complementary techniques that are really useful not only for glasses, but you can also use them for crystalline materials as well. Okay, so I think we're about on time. But in terms of a summary, I don't really know how you sum up MOFs. I was really struggling to think of a summary slide because, like, how can you summarize a field that has about 5 million things going on? But essentially, in case you forgot, they're porous materials and they're made by bridging these metal ions and linkers to form these framework structures that got typically large internal pore diameters and surface areas. We can tune this in a bunch of different ways, whether it's metal centers, linkers, etc., to use them for a bunch of different things. They've got a lot of uses. We've gone through a few of them, and all of this is driven by the fact they're very tunable. Their chemistry is tunable, their porosity is tunable. Advantages, they're typically quite high surface areas, so they're good for things like gas sorption. They're very tunable and very versatile. In terms of challenges, we do have some issues with stability. So we spoke about ZIFs, they're generally okay, but a lot of them are not really great when it comes to like difficult conditions, so like high heat or anything like that, sometimes water. In terms of scalability, yes, there's a lot of people who are looking at scaling these up, and there's a lot of companies working in that area. But, you know, it's still going to be hard to scale all of these materials, and also just the cost of synthesis. You know, it has to be on a par with what's already out there. So if you can get an activated carbon by the bucket load for like pounds, you know, are you going to pay hundreds if not thousands of pounds for the same thing for a MOF? So it's all about that balance and, you know, whether the cost of synthesis is actually worth it for your application. So in terms of future perspectives, obviously I'm here to talk to you guys about the CDT. Digital chemistry is really important. And all of this goes hand in hand with experimental materials chemistry. So all of the studies that I showed you had an element of computational chemistry, digital design, digital discovery. So the work I spoke about, we had to prove it by computational chemistry. You know, all the things where you did like absorption of carbon dioxide, all of these had to be proved, these interaction energies had to be proved by computational chemistry, etc. You can predict MOF structures by computational chemistry. So all of these go hand in hand, and we need digital chemistry to make new MOFs, figure out what we can use them for, take them forwards. So many companies are working in this area on MOF commercialization. There's quite a few. One of them, Orbital Materials, are using like AI, digital discovery to try and make new kinds of frameworks. So there's a lot of stuff going out there. So essentially, MOF design and discovery is very much a combination of experimental synthesis, computational design, and it's sort of like a cycle. So hence, the project that Matt is currently working on is this, you know, we're looking at this hand in hand of like digital discovery of glasses and then also making them as well. So we need a combination of both in all of these PhD projects. Okay, so thank you for listening. Any questions? I do realize that that was a very quick fly through, but if you want to ask more about MOFs, you can do. And we are MOF to a flame. So I feel like, you know, I'm part of a boy band or something when I say that. But we heat MOFs to a flame.
Thank you very much. Thank you, Lauren. Let me first stop the recording, and we'll have questions more informally.